Yeah, that's kind of the thing about this stuff, about this derivation, this differentiation. I'm sorry, that's different. This differentiation that we're talking about so far. Once you like get past the stuff of having to do it using limits and stuff like that, and you can just use rules, like the power rule, and the product rule, and the quotient rule, and stuff like that, all of a sudden, taking the derivative of surprisingly complicated functions turns out to be, wow, I can do this. It's not that complicated. And so we've been doing this for a while now, and we have been doing all of them that have so far been polynomial type functions. Polynomial functions as in they're of that form, f of x equals, well, there's like some constant times the power of x, then some constant times the power of x. A better way to write it would be that it's the sum of a bunch of terms, each of which has some constant in it, and then some power, where like I goes from 0 to some power, and there's a sum of terms. But you know, we know them when we see them. These polynomial expressions are things like, 2x squared plus 3x plus 7. I mean, another way to write that would be 7x to the 0 power plus 3x to the first power plus 2x squared, and so on. I mean, it's just an expression like that. We've also been doing a lot of them that were these rational functions, where like it's something, a polynomial in the numerator, and a different polynomial in the denominator. There, let's make it more something like that. And then we could just use the quotient rule. The quotient rule is the one that's a little harder to remember, but once you've got the pattern of Matt's yodeling solution, high d low minus low d high, is that right?
It's low d high minus
low d high, whatever.
All over low low.
I always remember derivative of the first times the second minus the first times the derivative of the second. I don't know. That's how we learn. Whatever works for you, I don't care. All right. And we've been doing this for a while. Now we're just going to add a few more derivatives that we can work with. And they're going to be the derivatives of the trig functions. So we're talking about derivatives of quantities like f of x is the sine of x, or f of x is cosine of x. And of course, there's 6 of those guys. Your book does take the time to actually derive one of those, as in to actually work through how would you determine, and it is done very much like those limits that we did, I don't know, 3.2 or something like that. But doing those limits, you might remember back when we learned that whole thing about limits, we didn't really do much that was like the limits of trig functions. We did a little bit here and there. They had to do a little bit of it so they could then introduce it here, but there's, I mean, let's not go nuts. Doing that big stuff of those limits of those trig functions is no big deal. But once you find out how to do it, you find out that in that case, the derivative of f of x for sine, derivative of sine, turns out to be the cosine. Derivative of sine of x is cosine of x. And derivative of cosine turns out to be, you would think it's sine, but no, it's negative sine. And these are by far the 2 most important ones of these trig rules for differentiation. These would be the most important ones. These are definitely worth your time to memorize. But they are just, and they're there in a little box. I don't think I have the right page in front of me here. Oh, I do actually. They're in a box on page 278. Hey, by the way, notice that they went back and they used a slightly different notation here. So they went and said, another way to write this is that the derivative with respect to x of sine of x is cosine of x. That's just another kind of notation, not using the little tick marks, the primes. And the derivative with respect to x of the cosine of x is negative the sine of x. So, I mean, this notation actually makes me happier as a scientist. This notation makes math teachers happier. Whatever. They're both ways of writing the derivative of.
Oh, that reminds me whenever we find the derivative of y with respect to x. Those are a little tough.
Well, yeah, I mean, it's just notation.
Yeah.
Yeah. So, like, if you had what Matt's saying there, like, let's say y was equal to the sine of x, then the derivative of y with respect to x is derivative of sine is cosine. They're all just ways of saying the same thing. I mean, here we're saying the derivative with respect to x of cosine of x. Here we're saying the derivative of y with respect to x. I mean, they're just different ways of saying, writing the same thing. That d by dx notation is useful in sciences. We talked about this once before, because equations might have more than one variable. In fact, in science in general, they do. You know, like we use the example of the ideal gas law, where the equation involves pressure and volume and the number of molecules and the temperature of the gas and so on. Well, what do you mean the derivative with respect to what? The derivative, is the t the variable here? Is the n the variable here? So this is a notation that makes a lot of sense in science. In math classes, since it's almost always just only one variable in the equation, who cares? Okay. The book actually takes the time too, a few pages farther down in another blue box, there it is, on page 281, to actually show you excuse me, the derivatives of the other 4 trig functions: tangent, cotangent, secant, and cosecant. I'm not going to write them down because they're right there in your book. I don't see any point in memorizing that kind of way here. So you could see that you've got like the derivative of the tangent is secant squared. The derivative of the cotangent is negative cosecant squared, and so on. Derivative of secant is secant times tangent, and so on. All of these, some poor lost soul somewhere along the way had to derive. And probably there are calc classes out there where they make them derive all these things too, but that's not so interesting. Well, it's not really so bad. The derivative with respect to x of the tangent of x. I mean, I suppose another way to write this would be that it's the derivative with respect to x of sine of x divided by cosine of x. Which, I mean, that's just a quotient rule thing. And Matt's going to sing the little quotient rule song again. Low-D-high or high-D-low? Low-D-high. Low, derivative of, okay, so low, derivative of sine is cosine, minus
high-D-low.
High-D-low, sine of x times derivative of that. Let's see, that's derivative of cosine is negative the sine, so we cancel that out. All over the bottom part squared?
Low-low.
Low-low. Which then would be, let's see here. That's cosine squared of x plus the sine squared of x all over cosine squared of x. Hey, anybody happen to remember what cosine squared plus sine squared is?
That's 1.
That's another way of saying 1, so this is 1 over the cosine squared. 1 over cosine happens to be secant, so this is secant squared. So the derivative of tangent is secant squared. Now we're the lonely, sad people who've had to derive this. Okay? I think the ones that are deriving sine and cosine are way harder. That's why we're not doing them. So anyway, they're on page 286, 287, I don't have my, 281. You have all 6 of the rules there. So, here's the deal about using an online textbook. You know, when you have a physical textbook like they're using in pre-calc, there's these pages at the front of the book that have all their calc identities, right, that they need for every test and every homework set and so on. But you don't have that. And as time goes by, you're going to get really, really tired of trying to figure out where in your online textbook that rule for the derivative of secant is. Or the derivative, or the product rule, or the chain rule, which is the next section, and so on. What are we going to do about that? I'm new to the whole business of using an online textbook. Even all my online classes all have a physical textbook they have to buy. What do you want to do? Should we make a sheet that we can have that would keep all of our equations like this in one place? Should we buy a textbook? Should I make a sheet that I give you? What would you... I'm glad Jared's not here to answer that question. Hi, Jared. What would be your preference as a way that we get something equivalent to the cover of the book, the back cover of the book that would have all these equations in it?
I'm sure there's probably some other cheat sheet, like that online already.
Probably. I was thinking that possibly Dr. Shragi would just, when he gets home, make photocopies of the inside back cover of his calc book when he took the class. And then we could just have them. Does that make sense? Because, I mean, I agree. I think that we should have those kinds of things. And you know what? Honestly, I've never looked. It could very well be that if we went all the way to like the back, you know, to the very end of this PDF, it's actually got some pages. Maybe I'll even check that before I print. But you know what I'm... Well, hell, let's go look right now. I don't see anything. Wait, formulas from geometry, formulas from pre-calculus, review of pre-calculus, hyperbolic functions, integrals. Ah, yes it does. Hold on, tables of integrals. Oh, nope, they don't have one for derivatives though. Okay, they do have the tables of integrals though. That will be useful to know later. Okay, in and of itself, these 6 little equations are no big deal. I mean, there's 6 little things to either memorize, write down in the front of your notebook, find a place at the back of the book, wherever, write on a piece of paper. Those 6 rules are no big deal. What we're actually going to be doing with them is using them in a more complicated equation. Let's do one. How about if I gave you an equation that was, how about my function was 3 sine x cosine x. Take the derivative of this function with respect to x. All right. The derivative of this expression, we'll write it as f prime, is equal to, well, this is really just a product, right? It's 2 terms multiplied by each other. The product rule is going to be just fine. So let's see. How about if I made this 3 sine x, well, let's rewrite this up here. How about this? 3 sine x, that'll be one of my terms, and the other is cosine of x. Alright, so my product rule tells me that it will be the derivative of the first term, I'm going to write it this way with a tick mark by it, times the second term, plus the first term, times the derivative of the second term. Okay. The derivative of 3 sine x. Well, we can just pull that 3 out, so it's going to be 3 times the derivative of sine. Derivative of sine is cosine. Getting ahead of myself there. Times, then, so this became this. Times the cosine, plus 3 sine x, that's this term right here, times a derivative of the cosine. Oh, this tick mark should be on the outside. Derivative of the cosine. Derivative of cosine is negative the sine. So sine, we'll change this to a negative sign right here. Hey, look what we got here. 3 times the cosine squared of x minus the sine squared of x. Man, we came really close to having something interesting there where we would have had sine squared and cosine squared, and we would have gotten all kinds of more terms to cancel out, but this one it didn't work out that way. So the derivative of this is equal to this. Now, wait, let me be clear about that there. Sometimes students will write this all out in like one line, and that's a mistake. Don't go, let's see, so f of x equals 3 sine x cosine x. And let's see, I want to find the derivative of that, so that's 3 times, after a bunch of more steps, cosine x squared minus sine squared x. Like this. No, this is not right. Those things are not equal to each other. That is the derivative of that one. It is the slope of that function at any number of different places. So, you know, like if we wanted to know the slope, the rate of change, if this was describing something, this was a function that described, I don't know, the position of some particle, then this is the one describing its velocity at any given time. Like we did on the last homework set. All your rules worked just fine. I mean, that was product rule. Your rules for addition and subtraction work just fine too. Like f of x equals, how about sine of x plus tangent of x. Then the derivative, heck, I'll just mix it up a little bit by using the other notation. D by dx of f of x will be equal to derivative of the first term derivative of sine is cosine, plus derivative of this term. We can just add up the derivative of this plus the derivative of that. Derivative of tangent, I think we decided was secant squared, didn't we? Secant squared? I think so.
Yeah.
Okay, so our rule for adding terms, I mean, we just have, works just fine here too. We can do that with trig rules, no problem. Our quotient rule works just fine too. Let me mix it up again. How about f of x is equal to some fraction? How about sine of x over x squared plus 1? It's just some function that's a fraction. So to find its derivative, f prime of x, we're going to need to use the quotient rule. All right.
Low di.
Low di. Okay, so low, the denominator, times the derivative of the numerator. Derivative of sine is cosine, minus high d low sine of x times the derivative of the denominator. What's the derivative of x squared plus 1? 2x all over the bottom part squared. And then we might have some algebra then. In fact, my guess is we would, in order to get the answer in the back of the book. You'd probably have to like distribute this and so on. Hey, real quick, sine of x, the quantity, times 2x. I know it's tempting to make that like the sine of 2x squared or something like that. No. Right, that's outside of the sine. That one is inside the sine. All your rules work. And they're going to make you flex some intellectual muscles to show it. Let's see. Hey, that's the wrong class. Hold on. No. I don't know what I'm doing. Where'd it go? Drive. Calc. All right. Page 285. It is numbers 175 through 201I. Some of these guys, oh, by the way, all of you guys show your work. Okay? I don't want any business of like people just wrote down answers from the back of the book. Some of them say things like, use your graphing calculator to make a graph of, okay, I don't care about that. Okay. I mean, yes, that's lovely if you do that, but you don't have to. Okay, that would be educational, but I don't want to help. I don't want to see 7 different calculators. You know what I'm saying? All right. One of the problems in there is quite curious. It says something like, here's some equation. F of x equals, let's just say x cubed. I don't remember what the equation is. And it says find the value of x where the tangent line is parallel to y equals 7x plus 13. Okay, these are obviously not the right numbers, but that's what the kind of thing it's asking. Y equals 7. What is it even asking here? So we could make ourselves a graph of this function. Graph of x cubed is something like this, isn't it? I think so. So what it's saying is there is some place here where a tangent line is parallel to some other tangent line. I'm sorry, it's parallel to some other line. What does it mean to be parallel?
Have the same slope.
They have the same slope, yeah. So what you really mean is you want it to have this slope, which in this case is 7. So, all right, so the tangent line will be from the derivative. We'll need to know the derivative of x, f prime of x. Well, that's 3x squared. So you're trying to find the values of x where 3x squared equals 7. What?
X equals 2. That'll equal 7.
No, is that 3 plus x squared?
No, 2 times, oh yeah, you're right.
Yeah.
You're right.
So we would divide x squared equals 7/3. And I say I just pulled these numbers out of anywhere. So it's not such a nice round number. But you see what I'm doing here, right? So if we were to say at x equals square root of 7/3, and curiously, actually over here at the negative one, at x equals negative 7, square root of 7/3, then at those places, the tangent line is parallel to the one that they gave. I thought that was kind of a clever and interesting problem. All right, although usually I don't care about clever problems like that. Okay, I think you have what you need to get this one going, and I'll be glad to answer any questions.